Okay. Einstein's equation. Write that down. Oh, you got it already. Good job. Come on, guys. You ready? Chop, chop. What you got? Cappuccino? Americano?
Americano.
Americano. Ready? Okay. There's quite a bit to look at. Okay. Because the mass of a proton and a neutron are so small, we do not use kilograms. Because kilograms is too big. Just too big. Instead, we use a smaller unit. The gram? No, even the gram is too big. We use a unit called the atomic mass unit. Or you could write it as U or AMU. Okay? And the definition is this. 1 AMU is this many kilograms. So you see it's very, very small. Now the reason we use this is because we can say a proton is about 1 AMU and a neutron is about 1 AMU as well. So it's a good unit for small masses. Okay. We might have talked about this before.
I saw so many students, they just this way to write. It's better.
Which way?
I always this way, just straight and some straight.
Oh. Yeah, I like to be at an angle.
Why?
You too.
Why?
But they like straight. I don't know.
It's better?
Personal. Alright, you got that? Yeah? Yeah? Okay. Note the mass of one proton and one neutron, they're about 1 AMU. Okay? Now, I want you to look at the following reaction. What is this here? This is one proton. So what is this guy? It's hydrogen, yeah? What's this one? Lithium. Now, when you hit a hydrogen and a lithium together, they'll make 2 heliums. Okay? So let's check this. How many protons here? 1. How many here? 3. And how many here? 4 in total. That's good, right? How many neutrons here? Or no, sorry, how many nucleons? 1. And here 7 and here 8, which is correct. Okay? 0 neutrons and 4 neutrons. All fine, right? Now, is this balanced? It seems to be. But let's look at the masses. This is the mass of hydrogen, 1.007 AMU. This is the mass of lithium, 7.016 AMU. And this is the mass of helium, 4.002 AMU. So, what I want you to check for me, I want you to add these two masses together and tell me what you get. Well, you can see it here. It's 8.023. Okay. 8.023. Right. What is this mass here? Ah, it's different. Is it more or is it less? Less. So where did it go?
Air.
No.
Release. Release.
No. Not released. Everything is contained. No release. So you might think maybe we missed something here, but we didn't because it's all balanced. So what's going on here? Mass does not just disappear, right? Or can it? Can it just disappear? Okay. So if we look at this, we want to know what is going on here. So
Gamma.
not gamma. Gamma has no mass, but that's a good guess. That's a good guess. Now, this experiment was done by Cockcroft and Walton, and this is what they did. They took hydrogen and lithium. So they had some lithium, and they fired hydrogen at it, and they made helium, the helium gas. And they calculated the masses, and they discovered some of the masses lost. Now, before I continue, I think this reaction, you should write it down as an example. And if you would like to, you should write down the name of the experiment. It came from the Cockcroft and Walton experiment. Okay? Yeah? Yeah? So, why did Walton do this experiment with Cockcroft? They didn't just wake up one morning and decided to do this experiment. You know, they didn't wake up and say, let's fire some hydrogen at some lithium. What they were doing was they wanted to prove a formula, and this is a formula that they read from Einstein. Einstein, you know Einstein? Yeah. Einstein predicted that when atoms combine in a nuclear reaction, some of the mass will appear to be lost, but it's not lost. Rather, it's converted into energy. So Einstein said, when you take two masses and put them together, some of the mass will be lost, but it's not really lost. It was converted into energy. So this is because of Einstein's formula. Einstein said the energy will equal mc squared. This is Einstein's famous formula. Or you can just write it, E equals mc squared. You have seen this formula maybe on TV before.
C.
Speed of light.
Okay.
Yeah, have you seen this formula before? E equals mc squared. This is famous formula. It's like Newton's F equals ma. Yeah?
So we can change the mass to the energy.
Yes. Amazing. Right?
And
And then you think, can you change energy into mass? Pretty amazing, I think. Don't you think?
the sci-fi movie
Yes.
energy.
Yes. Yeah. Just like the sci-fi movies. Correct. It's quite amazing. You can change mass into energy. You can change energy into mass. You don't look amazed. Is this not amazing?
We eat too many food every day, and the food give us energy.
Yeah,
I think
but
it's everything.
no, because the mass is the same.
Yeah.
If you eat 1 kilogram of food,
Yeah.
you will have 1 kilogram of poop.
No,
Okay.
no. It's
1
really-
kilogram
Well-
of poop. God.
No.
Sorry, not just poop, but also
Yeah, I know.
front as well.
Yeah.
Yeah. No, but
But
Okay.
It's
the
like
energy you will, the energy will go into your body and make you do anything.
yeah, but it's not because you're losing the mass. You get that energy because the mass changes from food to poop. So the energy is taken out.
Yeah.
Yeah? So what I'm trying to say is in this Einstein's formula, the mass is gone. Like, I give you an example. Like, if I have a piece of wood, okay, a piece of wood, and I burn the wood, I get heat energy, right?
Yes.
But I don't lose any mass. Because although this disappears into ash, the mass is still there. It just turned into ash and it turned into smoke. But if you took the mass of the smoke and the mass of the ash and add them together, you will get back the mass of the wood. Do you understand? It's the same with the food. If you eat a hamburger and do some work, and then you measure how much mass comes out of you, it will equal the hamburger. If it is equal to less than the hamburger, it means some of the mass was turned into fat. Okay? And if the mass was more, then it means you lose weight. You know? But the mass is still the same. Ben thinks it's amazing. That's okay. You don't think it's amazing. Do you think it's amazing?
I don't know, but it's similar with. I watched some movie before about a lot of things, but the scientists say the things not from nothing, the stuff not from nothing to create it.
Yes. This is mass. This is mass. This is mass. This is mass. Okay. Before this, and this were mass. Originally, many years ago, it was energy. So first it's energy, then the energy becomes mass. So what we're doing is you can change the mass back to energy. Is what we're saying. Okay. Right, did you write this formula down?
Yeah.
Okay. So, let's do a calculation here. This is back to the Cockcroft and Walton experiment. Okay, so let's look at a calculation here. The mass of the proton is that. Now, I said 1.007, but let's be more accurate. It's 1.007276. Okay. The mass of a neutron. Oh, sorry, that's the wrong thing. Sorry. No, I'll be more precise later. Let's just use these numbers for the moment here. So let's calculate how much mass we lost. So the mass at the beginning, we said, what was it? 8.0023.
0 to 3. No, just 1 0.
Oh, sorry, thank you. AMU. And the mass afterwards is 8.004. So the mass that you think you lost
1
is 0.018?
No.
9 AMU. But you didn't lose that mass. It actually just became energy. So yeah, like gamma, I suppose. It's like an energy, yeah. But usually it's like heat energy. It's very hot. Yeah, okay. So according to Einstein, this will be 0.019. That's the M. But it's AMU. What did I say AMU was?
1.660.
We'll just say 1.66 times 10 to the minus 27. And then we have to multiply by C squared. And C is about 3 times 10 to the 8 squared.
What is the speed? Or why is C?
Speed of light.
Why is
Huh?
why we multiply speed
Yes.
of light?
That is a very good question. Why is speed of light in this formula? And I'm sorry to tell you, the proof is too difficult for you. I'm so sorry to tell you. But you can prove this in university.
Okay.
It seems very strange that light should be in this formula, but it is, and you can prove it. But the proof is like 3 or 4 pages.
Oh.
You see, Einstein was very smart. You know, he was very smart. Okay, can you calculate this, please?
No, like E is 35.
No, you typed it in wrong, I think. Yeah, that looks like it. 2.8386 times 10 to the minus 12 joules. Did you get that too, Summer?
2.83.
Mhm.
Yeah.
Now, because this is so small, I think it would be good to use electron volts. So if you could divide that by E, please.
One point 0.04
Yeah.
minus 10 minus 12.
What? You divided by the wrong E. That's the maths E. We need the physics E.
Oh, it's physics.
What was it, like 1.67 or something? Times 10 to the minus... It's the charge of the electron. 1.67 times 10 to the minus 23 or something, wasn't it?
Mass?
Charge.
Charge. So 1.602 times 10 minus
19, sorry.
is charge of...
Yeah, charge of electron.
So is this divided?
Mhm.
Okay.
6.3,
Yeah.
6.4.
Okay. But still pretty small. I think maybe you mistyped. Yeah, I think you mistyped. So I got 17.7 mega electron volts. Now, look, when you're ready. Did you write this down?
Mega. Wait. I get the...
1.3, yeah, good sense.
But is this... One? Oh, yeah, wrong. I lose the brackets. Yes. So it's mega is 12 and 9.
6.
Oh.
Now, I know this looks like a small number, but it's actually a very big number because this is a very, very small mass. I mean, this is a tiny mass, much less than one atom, one proton, right? And you get quite a lot of energy for its size. 17 mega electron volts. It's actually quite big, and we'll see that more later. Okay, continue. Yeah? Yeah. Now, this is the mass of a proton. This is the mass of a neutron. Oh, that's the wrong way around. Sorry, it should be 1 on the top and 0 on the bottom, right? Yes? That's the wrong way. The mass of 2 protons and 2 neutrons together is... So, this is a proton. This is a neutron. The mass of 2 protons and 2 neutrons. Proton, proton, neutron, neutron is this. Right? Fine. In fact, if you do measure it, you don't get this number, you get this number. So, think about this. You have 2 protons, 2 neutrons. You stick the 2 protons and the 2 neutrons together. The mass should be this. But it's not. Instead, it's this. So, that's very strange, isn't it? It's like if I took this, maybe this is 1 kilogram, and this is 1 kilogram.
2 kilograms.
I should have 2 kilograms, but instead I have 1.99. And then I separate them. Now I have 2 again. That's strange, right? That's very, very strange. So, again, 0.2928 is missing. This is called the mass defect, the missing mass. Now, before I continue, I think you need to write down that word at least. Mass defect is what you might call the missing mass.
you said if we move that together and they lose some
Yeah.
mass, and if we
Separate.
separate again,
The mass is back. Yeah. It's pretty strange, right? Right? Pretty strange. So, why is that? Well, that's because of something called the binding energy. So, let me explain. If you have a proton, and you have a proton, and you have a neutron, and you have a neutron, yeah, you could stick them together, and you could stick them together, and you'd have proton, proton, neutron, neutron. Fine. However, what charge is a proton? Positive. And what charge is this proton? Positive. So when you put them together, what should happen? Should they stick?
No,
No.
push.
Just push. But they do stick because this is helium. So why can they stick? So what happens is the two protons are trying to push away. So there's some energy that keeps them together, like a force that holds them together. But then where did this energy come from? This energy came from taking some of the mass. So you have two protons, you put them together. Some of their mass gets turned into energy. This energy keeps them stuck together. That's what's happening.
But how it get back if you grab
Yeah, so when you separate them, the energy is no longer needed. So the energy goes back into the proton and becomes mass again.
because the energy, how the energy knows is belong to which proton.
That's advanced physics. You're not ready for that. That's university level. It's very complicated. It's very complicated.
So the energy knows where they will go.
Yeah. This is not easy to understand because it almost looks like the proton and the neutron has a mind.
Yeah.
It really looks like this. It's very strange. So, the binding energy of an atom is the energy you need to hold it together. Okay? And this energy E, the formula to calculate it is equal to mc squared again, where m is the mass defect, the missing mass. That is the lost mass. Okay, so I would like you to write this definition down. got that? Now, what's interesting is when you have the two protons stuck together, you need to, if you want to separate them, you need some energy, right? Because they're stuck together. How much energy do you need? It's the same energy. This is also the energy required to separate the nucleus. Okay? It's the same energy.
So, if you separate them, you still need energy. Why the mass going back not lost to double of it?
Yeah, we can. Okay, let's look at it now. I suppose go. Yeah, a bit complicated, but. What you're doing when you separate it is it's like you're using your energy to cancel the binding energy. I'll give you an example, a simpler example. So, here you are, and here's the car. The car's heading this way, and you're heading this way, and you stop the car. Let's just pretend you stop the car, okay? How much work or how much energy do you need to stop this car? You will need the amount equal to the kinetic energy. So if this has a kinetic energy of say 1,000 joules, then you will need 1,000 joules of work to stop it. But when the car is stopped, the energy now is 0 and 0. So it's not like... So I suppose this 1,000, where did it go? Well, it changed into heat and other things too. I'm kind of trying to say the same thing with the nucleus, okay? There's like two protons here, and there's energy sticking them together. Let's say the energy is 1 joule. If you want to pull them, if you want to pull the protons apart, you will need 1 joule of work. Okay, but if the protons separate by themselves, then they will release 1 joule of energy. If they do it by themselves. Yeah? Yeah? I know, it's a bit confusing.
Like human.
Yeah. 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 It is very much like they're human. Continue? Right. In an earlier lecture, we saw that the weak nuclear force is trying to push apart the nucleus. Newton's law tells us that if the atom is not decaying, then the net force should be 0. Therefore, there's a counterbalancing force called the strong nuclear force. So, you learned that inside your atom, your nucleus, maybe proton, proton, neutron, neutron, there's a force trying to push this out. Do you remember this? And we call this the weak force. And this is the force that makes radiation. This is the force that makes alpha, beta, and gamma. Okay? But do all atoms decay? No. Only some of them decay. Like uranium. Uranium decays. What else? Plutonium. Carbon-14, these decay. But, you know, something like H2O, does that decay? No, it's stable. Okay? Why is it stable? Because there's another force the other way called the strong force. And if the strong equals the weak, then it's balanced. Okay? If the weak is more than the strong, what happens? We get radiation. Alpha, beta, and gamma radiation. So what do you need to know about the strong force? The strong nuclear force is, number 1, strong. Number 2, attractive, meaning it pulls the nucleus together. Number 3, it only works on a small distance, 10 to the minus 15 meters. And number 4, it is the force responsible for binding between protons and neutrons. Okay? How does an electron stick to a proton? The electron sticks to the proton because the electron is negative and the proton is positive. But how does a proton stick to a neutron? Or how does a proton stick to a proton? Because of the strong nuclear force. Now, wait, before you write it down, please note, in the exam they will ask you for 3 things.
Wow.
So I've given you 4 things. I've said it's strong, attractive, short range, and it's a binding for it's responsible for binding. They need 3.
All fat.
Huh?
All fat.
What?
All fat. So you those all fat.
Off F? What are you talking? What?
The second line. All fat. Second
Ah!
Yeah. See?
Of an atom. Thank you. Your English is very good.
No, no.
Yeah, somewhere spotted. It should say, second line, the nucleus of an atom. Summer's grammar is so good. Because he's going to all his EAP classes now. Right? Yeah, good man. On time?
Yeah.
Yeah, good.
And last time to sleep.
And what's that?
Last time to sleep.
You're sleeping less?
No. Last time.
Last time?
Less.
Less?
Yes.
What do you mean less? You're not sleeping?
Before. Last time before.
Oh! In class? You're sleeping less in class?
Sleep less. In my home.
But that's a bad thing.
Yeah.
Why are you sleeping less? Because you're studying?
No, because I have to come to school on time.
Oh! You're sleeping less because you're coming to school. Yeah, good for you. Alright, continue. Right, so let's do a calculation. What is the binding energy of helium? Okay, so how many protons in helium is helium-4? How many protons? Protons. 2. 2
Oh,
protons.
sorry.
How many neutrons?
2.
2. So, can you use this to calculate the binding energy? First, you need to calculate the mass. The mass defect. Okay? So, the mass is 4.002, but that will be smaller than 2 of these and 2 of these. Okay, can you try to calculate it, and then we'll do it together. See if you can calculate it. You have to understand, you have to first calculate the missing mass. So what you do is 2 of these plus 2 of these will not equal this.
0.029.
Good. So that's how much mass is missing. So then somewhere what you should do is multiply by U and multiply by C squared. must have done
Oh,
something
no,
wrong.
no.
Right, but first, let's see. What is the m? So that will be 4.002. No, sorry. It will be 2 times 1.007 plus 2 times 1.008665.
4.03133.
Great, just one sec. So this is what it should be, right?
Yes.
But this is what it is. So the mass defect is, yes, Summer?
0.02933.
So then the energy will be 0.02933 times U times C squared.
Yes.
What's that, Summer?
What is U?
AMU.
Oh.
What's wrong, Gav?
So, what's the second one? The n, small n, the 1.0086.
Neutron, is it? Neutron, yeah. 4.38 times 10 to the minus 12 joules. Now we usually write this in EV.
So what's the EV?
It's the charge of an electron. It's in your notes.
It's U.
I think I have EV class.
Thank you.
So that's my question. Where change the ratio to convert EV.
Yeah.
Which. Oh, no, it's not. Yeah. We'll say is EV convert to joule is
Multiply E
5
and
joule.
to EV divide E.
Okay.
Yeah, it's okay? Gail, it's okay? Are you sure? Yeah? Continue? Yeah. So look, next is the same question, but I want to know what is it per nucleon. Per nucleon. So let me explain. Imagine you have 4 nucleons and the energy here is E. And here, let's say, you have 8 and the binding energy is 2E. You might say, oh, this has more binding energy. Well, yeah, but the only reason it has more binding energy is because there's twice as many. So what's more important to know is not the binding energy, but the binding energy per nucleon. So because you have 4 of them here, what we usually do is divide this by 4. So if I divide this by 4, I get 6.85 MeV per nucleon. That's usually what we want to know. See if we can add that in. Yes, go. Continue. Summer? Yeah? Okay, good. Right, now, here is a graph that you need to know for the exam. They sometimes ask you to draw it. Let me explain. So, what you have on the x-axis here is the number of nucleons. So, for example, if you have one nucleon, that means you have one proton, which means you have hydrogen. Can you see here? Hydrogen. If you have two nucleons, that means you have possibly H2, which is one proton, one neutron. Can you see there it is H2? Okay, and it continues. You see down here is 238, uranium 238. It has 238 nucleons. Yeah? So what is this graph? On the x-axis is the nucleons, and on the y-axis is the binding energy per nucleon. In other words, can you see here this number? Okay, so for example, if I go to, I can't quite see, but if I go to 4, there's 20, there's 10, 4 is about here, I should get 6.8. So, you can't really see, but like it's going to be like here, about 6.8 for 4, roughly. Okay. So, what's this graph saying? The more nucleons you have, the more energy you need per nucleon. But then at this point, it starts to go down again. So this here is the most stable material. It's the most difficult to separate. And can you see what that is? Fe, which is iron. So iron is the most stable and the most difficult material. You can't separate the nucleus very easily. The most difficult to separate. Okay. We call this half of the graph before iron the fusion, and we call this half of the graph the fission graph region. Okay. Now in the exam, what do they need you to write? They don't need all of this. Okay. They just need you to have a shape like this. I'll try and draw it for you here. So here is the nucleon number, okay, and here is the binding energy per nucleon, okay, and the graph you need to draw should go up like this to a point and then slowly come down. And then you need to mark this one off as Fe. Can you see? Which is, you can't quite see that, 56. And then you call this side here, you can see fusion. And then you call this side here fission. Yeah? Okay?
S-O-N?
Huh?
Fission.
Fusion and fission, there you go.
F-I-S-S-I.
There you go. Okay? Yeah? Yeah? Son, what's so funny? No, show me.
No. I won't understand this.
Chinese joke? Dirty joke?
No, it's not.
Okay.
About slang.
Slang.
About accent.
Continue? Alright, no, that was the last thing. Okay, so, how many questions did I give you for that one?
So
Only 3. Good, good. Oh, do we need to check any answers? What was the last lesson?
this
Oh, that's fine. And what was the lesson before that? Do you want to check those answers? Let's have a look.
oh the
You check.
graph nice one.
Excuse me. We are going to check the answers for this one.
Alright.
Right. So, you drew your graph. Okay. What did you get for lambda in part B?
Lambda oh
3.56.
What did you get?
Maybe it's not this questions.
Are you doing? Look, this one. This one.
Yeah.
What you get for lambda?
I didn't write here.
Oh, what did you get?
0.17.
Good, good. What did you get for the half-life?
3.96.
Good, okay. And what did you get for N0?
28.6.
Okay, and what you get for the next one?
264.
Oh? Yeah? You might want to check that one.
Okay.
Yeah. Okay, so it looks like you're alright. And what about the lesson before that, half-life? So we got to the one before that.
No.
Not finished?
No.
Why not?
Oh no. Because we just talk about this and come back this and
Oh, so you need to finish this. But we did this, didn't we?
you which
Half-life.
yeah we just talk
Yeah, but it's not finished.
yeah.
Did you do? Did you do anything, go? Oh, go!
I think we can and you talk about the answer.
No, this one, half-life.
No.
No, okay, fine. Oh, but the one before it, did we check the answers?
Yes, I think because I write.
Okay, good. Fine. So, how many worksheets do you have to finish? You have half-life and the one for today, so you have 2 to do. No, that's okay, 2. Fine. Khalifa, how many? Where's your book?
Where's the laptop? Listen.
Oh, but I said the laptop's Friday. Okay. How many worksheets do you have to do?
Me?
Yeah, you.
That much.
Yeah, how many is that? Count for me, please. Oh my goodness.
5.
What?
5.
12? Summer, how many worksheets do you need to do?
I don't know.
Cool.
Maybe. One, two, 3, 4, 5.
Okay, stop. It's okay.
8, 9, 10, 11.
11, 12, 2. How many of you to catch up on? Hmm? You guys are...
I should say I have 6, 7, 8.
Look, Summer, put that phone away. I'm angry at you. Put it in your pocket. Okay, all of you have lots of work to do, and you're not doing it at home. All right. Okay, I'm not going to do another lesson because then you'll have more work you need to do. You have 2 to do. That's fine. I'm not angry at you. But you three, I'm a little angry at you because you have so much to do, right? So much to do. So, you can start on this lesson and go backwards, or you can go the other direction. What do you want to do? Backwards or forwards? Do you know what I mean?
No.
You can start with today
Yeah.
and go backwards,
Yeah.
or you can start from the past and go forwards.
First one.
Go backwards.
Yeah.
Go backwards, okay. What one are you going to work on?
Fine.
You're going backwards or forwards?
Fine.
You're going backwards. And here, Khalifa, you want to work on today's one? Okay. Oh, well, Ben's working on today's one, so you can just share there. Work hard. Okay, come on, go.
No, the problem is
The problem is you.
I need listen to class first and finish the work.
Yeah.
You got what I mean?
Huh?
That's all the class that we're missing.
Yeah.
So I need listen class first and finish.
Okay,
the
fine.
work.
But for today,
Yeah, I'm
you can do
finished
this. And did you do Half-Life? You didn't do this. And you didn't do this. What? What's? Oh, come. Okay, come on.
That's all the class that I'm missing.
No, you weren't missing this week, were you?
But this week, that's the first physics we have.
This is the first physics?
We have 2 days maths
Oh,
for class.
okay, fine. Oh, because you were in Turkey. Right, well, start on this one now.
Yeah.